Okay, as promised, the last two questions from the myAP stuff. These are the lengthier ones that I did suggest, and a lot of you started to do this. Upload one document. If I do these in the future, you can just do that. Upload one page, put it in part A. As long as I see all the parts, it's easier for you, it's easier for me, and it's just a lot easier for me. So anyway, here we go. Questions 5 and 6. And we'll start with number 5, I guess. It makes sense. So number 5 gives us a chart of values for lots of derivatives of this function f, all of them at x equals 3. And the first question that we are asked is to write an equation for the tangent line, use it to approximate a value. Well, what we know about tangent lines is that what we need is a point. So we need to know what f of 3 is. Well, f of 3 is 6. We also need to know what its derivative is, and the derivative of 3 is negative 10. That combined with the single point, well, that's it. All we need is y minus the y value, so y minus 6 is equal to the slope, x minus the x value, and you could stop there. You could go ahead and add the 6 to both sides. Whatever it is, there's the tangent line. We're approximating f of 2.5, so this is y, which is the same as f, so f of 2.5 would be approximated by negative 10, 2.5 minus 3, so negative 0.5 plus 6, and that's going to get you 5 plus 6 is 11. And that's it for part A. Part B says, let's go ahead and write the third degree Taylor polynomial. And let's just start with that. Then they ask you some follow-up questions. So for third degree Taylor polynomial, we're going to go ahead and set up our little chart here. 0, 1, 2, and 3. And we're looking at f of x, f prime of x, second derivative, and third derivative. All of these are going to be at x equals 3. We're going to multiply by our factorial, and then we're going to multiply by the polynomial x minus 3, because that's where we are, to the nth power. All the values here coming right off the chart, so we go back and look at the chart again. It's going to be f of x is 6, so 6, negative 10, 16, and negative 24. So we said f of x was 6, f prime negative 10, f double prime 16, and f triple prime negative 24. 1 over n factorials times 1, and 1 and a half, and 1/6. You should kind of almost be just not even thinking about those numbers at this point. And then there's nothing here, and x minus 3, and second term, squared, and third term cubed. Putting these together gets us our polynomial of 6 minus 10x minus 3 looks like an 8x minus 3 squared, and finally 24 over 6 negative, so negative 4x minus 3 cubed. So that's the polynomial that we're looking for. We go back and let's look at our questions. Is there enough information to determine whether f has a critical point at 2.5? Well, remember what critical points are all about. The derivative here would have to either equal 0 or be undefined. That's when critical points are going to occur. And we have our approximate function here. We have our approximation for the function. The problem, though, is that we're looking for information at 2.5, and all we have is something that is guaranteed to be true at 3. It's an approximation as soon as you move away from 3. Plugging in 3 obviously gets me zeros down the line, gets me an exact value. Beyond that, anything at 2.5, it's an approximation. And that's not going to be good enough. So we don't know whether these things are going to actually happen if all we have is an approximation. Therefore, we really can't answer the question So we're kind of in a neither case because we just can't even tell. There's not enough information. Not enough information. Last question here. What's the coefficient of the x minus 3 cubed term of the Taylor series for the derivative of f? So in order to figure out the derivative of f, we really could just go ahead and make a Taylor series starting kind of over again. I'll put it down here in the bottom corner. We're looking at 0, 1, 2. We're looking for the coefficient of the cubic term that's going to come from down here. We start now, though, not with the function, but we start with the thing we want the Taylor series for, which is the derivative. So we're going to be offset by 1 here. So it's going to be a fourth derivative at this point, but that's okay because we know the fourth derivative. The fourth derivative, wondering why they gave us that, is 32. This one gets multiplied, although it's the third, so we're still going to be looking at the 1, the 1, the 1/2, and the 1/6. This is going to be our coefficient. This reduces to 16 thirds. So there's your coefficient. And that's question number 5. Part C was a skip. It's not a topic that we needed to know this year. So that brings us to problem number 6. And in problem number 6, they give us a chart and they give us a graph. And again, we're looking for Taylor series questions. So here we are, write the third degree Taylor polynomial. So let's go ahead and just set that up. We know how we start it. 0, 1, 2, and 3. And we're doing this now about x equals 0. So we're going to be looking at f of x, f prime, double prime, and triple prime. We need to note these values are sitting at x equals 0. So if we come back up, f of 0, and the graph here is a graph of f, so f of 0 is 3. Read right off the graph. F prime is the slope of the tangent line. Well, here's the tangent line. And if we kind of look at where it's passing through, it seems to go down 2 over 1 pretty regularly. That's a slope of -2, directly from the slope of the tangent line. F double prime, well, now we're over here. When n is 2, the second derivative at 0 is 3. And the third derivative, n3, is -23 over 2. We're doing all these at x equals 0. There are our values. We're going to multiply by our factorial term, which is a 1 and a 1 and a half and a 1/6. At x equals 0, we are just going to be multiplying by x to the various powers. Here's squared and here's cubed, always matching. This gives us our polynomial. 3 minus 2x plus 3/2 x squared minus 23 halves times 1/6, and nothing cancels, so it's minus 23 twelfths x cubed. This is our approximation for f of x. And that's all we're looking for. Good. So we move to part B. It says, write the first 3 non-zero terms of the Maclaurin series for e to the x, the first 3 non-zeros. So we're looking for a Maclaurin, which is a Taylor, so 0, 1, 2. That should get us 3 terms. It's just e to the x. So our function is e to the x, and so is every derivative. We're doing these at x equals 0. E to the 0, these are all 1s. Our 1 over n factorial is a 1 and a 1 and a 1/2. And we're at x equals 0, so we're looking at x to the 0, which is 1. X and x squared. And this gets us 1 plus x plus 1/2 x squared. This is e to the x approximated by a polynomial. Then they're looking for the second degree Taylor polynomial of this product, e to the x, f of x. Second degree, highest being squared. There are 2 ways to do this. One of them is to create a new table, 0, 1, and 2, and now work with e to the x, f of x, and take a look at derivatives and use product rule to expand them. But there's another way to do this that I want to show you, and that is we're looking for e to the x, f of x. Well, here's e to the x, and here's f of x. I'm going to just copy it down from up here. 3 minus 2x plus 3 halves x squared. I'm going to stop there. This term's cubic. I don't need the cubic term because we're looking for a second degree product. If we multiply these two polynomials together and only consider the terms that are quadratic or lower, we'll have our answer. So let's see what we get if we do that. We get 1 times 3. We get 1 times negative 2x and 1 times 3 halves x squared. Now I'll go back and I'll do the x's. X times 3, x times the negative 2x. And if I do x times the last term, that's cubic. Don't want that, so we'll stop. And finally, let's take this one multiplied by everything. I get a 3 halves x squared, and I'll get a cubic, and I'll get a fourth. So this collection of terms should be our answer. Let's see what we get when we combine like terms here. 3 doesn't combine, I get 3. Single linear terms, I get a negative 2x and a plus 3x. That's plus x. Finally, I got 3 quadratics. 3 halves plus 3 halves is 3. So these two together are 3x squared minus 2, so plus x squared. And that might have been the faster way to get to that result. Let's take a look at C. This is a lengthy problem. This is number 6. C is asking us now to use the Taylor polynomial we found in part A to approximate h of 1. So we are integrating the Taylor polynomial. So we're going to come back and take the polynomial we had, which I should come back up, and it's negative 23/12, so we'll throw that in here. We're looking for the integral then, h of 1 would be approximated 0 to 1. X is 1 here. And we'll put in our f of t, which is 3 minus 2x plus 3 halves x squared minus 23/12 x cubed dx. This is about as straightforward an integral as you can get because it's all power rule terms. Take the antiderivative, 3x minus x squared plus 1 half x cubed minus 23 over 48, because of the 4, x to the 4th, evaluated from 0 to 1. That's nice because I just need to plug in the 1 here. 3 minus 1 plus a half minus 23/48. And you're allowed to leave that alone. That's done. But if you'd prefer, it's 97/48. There's your approximation. And finally, part D. This was the tough one. We know that the Maclaurin series will converge to h of x. This is for h of x. This is the integral we just worked with. We also know the individual terms for h of 1 will alternate in sign and decrease in absolute value to 0. So that's a convergence for the alternating series test. And that's what they're going to go to here. They want you to use the alternating series error bound to show that the approximation that we would get up here differs by at most 0.45. And what we learned, what we saw, was that the alternating series error bound is simply the next term as an absolute value, but it's the next term in the series. Well, this was the last term we worked with. All we need to do is figure out what the next term would have been. That would have been the 4th degree. We need to come back here and figure out what that 4th term would have looked like. Well, it would have been the 4th derivative at x. And we go further up still, there it is. The 4th derivative, again, why did they give us this? We needed it for the last part. So that's going to be, I lost it already, 54, I believe. 54, the factorial term at 4 is 1 over 24, x to the 4th. That gets us a term of 54/24, x to the 4th. That reduces to 20. What does that reduce to? 54/24. 2 into there and 2 into that, and 3 goes into both of these as well. 9 over 4. So it's 9/4 x to the 4th. So the next term would be the integral of 9/4 x to the 4th. We integrate this, we're going to get 9/4 a 1/5 x to the 5th. That's 9/20 x to the 5th. Evaluated from 0 to 1, this is the same integral, and that's plugging in the 1, 9/20, which is 0.45. So it turns out the error, the most we could have been off, is the 0.45, and it comes by looking at the next term. That's it. Those were a couple of tough ones. I hope these helped a little bit. And we'll look at some solutions posted for the College Board stuff coming up very soon.